Hello one, hello all. Welcome back. We are finishing this first practice exam. Happy birthday to Mags for those watching. If you see her, make sure you wish her a happy birthday. But let's go ahead and go through this. So essentially, we're continuing on 7. It says put a circle around the cycloalkane with the most angle strain. And so this is the important idea here is that when we think about these rings, when we lock them in, right, we always have to have the proper bond angle. But when we do this ring, we're locking them in, right? So which one of these is going to have the most circle strain?
Is it 4?
No, it should be the 3 one. The 3 one's going to have the most angle strain.
Oh, okay.
And then the one with the least should be my 6-membered.
Oh.
Because remember, 6 is going to be my least hindered, right? And the reason for this is that if I think about a triangle, right, the interior angle should be 60, but it can still kind of bend itself a little bit, so it lessens that, but it's still pretty low. I think it's like 88 or something like that degrees. If you look at 3, it should be 108, which would be close to ideal, but due to the fact that it's a 3D structure, it has to change itself. And so the 4s are our 6-membered rings are the ones that minimize torsional and angle strain, right? I think angle strain is non-existent in a 6-membered ring. So that's why 6-membered rings are our most stable. They're easy to work with. Does that make sense?
Yes.
Okay. 6-membered rings are great. 5-membered rings are okay. None of the 3 and 4 are bad, and then all the way till you get to 12 carbons before it becomes viable again. Okay, so circle around a conformer with the highest energy, put a box around the conformer with the lowest energy. So when we talk about conformations, right, we talk about the fact that when we have, there's 2 general states, right? They can either be staggered or eclipsed. Staggered is when they alternate, okay, meaning your bonds and stuff are alternating. They're not directly behind one another. So here, as an example, which 2 are staggered? Which 2 of these are staggered?
2 and 4.
No,
Wait.
1 and
1 and
3,
3.
because they alternate, right, every 60 degrees. So 1 and 3 are going to be staggered, and I'm just going to write stag underneath and stag. Hey, Matthew. And so it's kind of funny because what's her name put a comment on one of the YouTube videos, Megan, and she said she responded like she was in a Zoom class. She was just watching the video, and I asked the question, and she responded. And she's like, "Wait, you can't hear me. This is a video." But staggered are always going to be your lowest conformation, right? So you immediately know that your lowest conformation is going to be between 1 and 3. When you have eclipsed, when they're on top of each other, those will always be the highest energy ones. So we will call those eclipse for short. So eclipse will always be higher in energy. And so now we'll take a look at the highest energy one. The highest energy ones are when the biggest substituents are next to each other. So hydrogen, methyl, methyl, hydrogen, chlorine, hydrogen. So none of the big groups, methyl, or chlorine, are across from other big groups. But here you have methyl, hydrogen, hydrogen, chlorine, hydrogen. Now that you have those 2 big methyls across from each other, they're eclipsing each other. That is a lot of steric hindrance. So that's going to be bad. So this is going to be the highest energy one. Does that make sense? So anytime you have these conformations, look for the eclipsed ones, and then the ones with the biggest groups directly behind each other, those will always be the highest energetic ones. For your other one now, for staggered, you basically want your biggest groups to be pointing opposite directions. So on this front carbon here that I'm going to put the dot on, what is the biggest group coming off of that carbon?
L.
It's the methyl here, right? What's the biggest one in the back? It's also the methyl. Methyls are your largest groups because don't forget, you also not only do you have the carbon, but you have the hydrogens coming off of those, right? So a lot of people make the mistake and say, "Oh, it's the halogen. It's the methyls are more steric hindered." So the chlorine and the methyl, they are opposite each other here, and that's good. But the best one is when your two biggest groups, the methyls, are pointing in opposite directions like that. So always figure out which ones are the biggest groups, and you want them to be pointing opposite directions like that. Does that make sense?
I have a question. I thought that like CL would be like the biggest group, just considering because it has like the higher mass. Because the methyl group would only be like around 18,
It's
but
in this case, are you thinking about naming when you think about that type of thing? So don't forget when we talk about atomic radius, and it is a good point, right? We think about where this atom is located. Chlorine is in a row below fluorine, but carbon is also like 3 rows over, right? So there's chlorine is a little bit bigger, but coming off of the carbon are 3 hydrogens. So not only do you have that first atom there, but then you
oh,
have those hydrogens coming off as well.
oh, okay, okay, okay. Yeah, it makes sense now.
Yeah, it would be like if you and Max were standing next to each other, right? You guys are pretty close in height, if I remember correctly. I think. Wait, wait, Mac, are you like 5'6"? I might be confusing your height. Did you say 5'9"?
I should be
5'8".
5'8". Okay, never mind. I thought you were close to the same height as Melissa. Melissa's very short.
I'm
She's
5'4".
5'2". What?
5'4".
5'4"? Okay. All right. Well, here, just imagine this. Imagine. This is actually perfect then. So imagine you stand next to each other, and I'm like, well, Mags is taller. But then imagine I got out like a half-foot ladder, which is kind of like the hydrogens, and now Melissa stands on it. Now she's the taller one. So it's the fact that it's not just one atom; it's the fact that you have those hydrogens, right? That's what makes it a bigger steric thing. She had a chart, I think, in one of those notes that I saw from your PowerPoints from the week that covered this, and you can see which one of these causes the biggest energy. So you can, you can confirm with yourself to make sure. All right. Now it says draw a chair conformation of cyclohexane showing all of the equatorial hydrogens. So I am just going to move down and I want you guys to do that. Draw a cyclohexane. I'll draw both conformations of the same thing. So I need to grab my phone because I have a message that I need to check. So go ahead and do that. I'll give you guys a minute or two and we'll come back and we'll do it together. Okay. So while you're doing that, I'm just going to draw the chair conformations. Oops, if I turn on the writing tool. Oof, those are some nasty looking chairs. Some bus outside my window. You can't hear it, but I can. Well, maybe you can. So either one of those is going to be the correct chair conformation. Right. So did you guys get in close approximation, right? You only had to draw one of these, so it wasn't. Matthew, how'd it go for you?
I think I drew it okay. I mean, it's sort of, some of them are a little bit off, but I think I got it.
Okay. What about you, Mags and Melissa? You guys still working on it? Didn't get it right?
I got it right. I just did like I drew the hydrogens, but in the equatorial position instead of axial.
Yeah, that's what they wanted. These are all equatorial. Yeah, I hope these don't look axial to you for that bad of a
No,
drawing.
no.
Okay. What about you, Melissa? How'd you do?
Honestly, still kind of pretty lost. With chair confirmations, if I'm completely honest, I thought it will only be 3 hydrogens.
So every chair conformation has 6 axial, 6 equatorial. So every carbon has 1 equatorial, 1 axial, right? So if I was to erase this whole thing, right, like this, and so if I was to draw, every position will always have an axial and an equatorial position, right? And so if you need to, if you are just so confused, draw every position and then erase which ones they don't want if you get so confused with that. But just remember that they have to have both on each carbon.
Okay, yeah, that makes sense now.
Okay. Draw arrows for each step of the following reaction. So you have to draw arrows. So we've done arrows right before, I think. So that was with resonance, right? So there are a couple different rules that we have to follow when we do our mechanism arrows. So when we do mechanism arrows, the biggest differences is that we want to make sure that we always start at an electron source, and we can break single bonds this time. So in resonance, we couldn't break single bonds. This time we can, however. All right. So what I always like to tell students, you kids, is that always think about what's changing in every step. So looking at my starting material and here, what's different between the two?
There's like an extra hydrogen.
Yep. So over the arrow is where that hydrogen comes from, right? So what actually grabs the hydrogen?
The oxygen.
And what part of the oxygen is actually grabbing the hydrogen?
The electron.
Yep, the electrons in the lone pairs, right? Don't forget that this oxygen has lone pairs, right? And this is something that I always, is that electrons is what does the dancing in organic chemistry. And in fact, in all chemistries, with the exception of nuclear chemistry, right? Electrons are what make things happen. And so when we do these reactions, we always think about what the electrons are going to do. So we have to start an electron source. So this lone pair is going to grab that hydrogen like that. Okay, that is going to be my first step. Now, next up, right, now that we've got there, because now that makes sense, it's going to grab that hydrogen. We're all going to be good. What is going to be the next thing? So what happens from between the second and third step? What's the big change?
You lose the water, H2O.
Yep. So are we breaking a bond or are we forming a bond?
Breaking.
Yep. And so you just figure out what bond you're going to break. And you start on the bond and you go to the, like that. Because you find the bond that's no longer there, and that's going to go onto the atom itself. Does that make sense?
Yes.
Okay. So now that we've done that, let's take a look between here and here. What's different?
The plus sign moved.
The plus side moved, but something else happened.
Oh, there's another single bond.
The methyl? Is that
The
it?
methyl. The methyl did what?
It magically appeared. Wait.
No.
No, it moved.
moved
It
across.
rearranged.
This is called a 1,2 methyl shift. We will learn more about that when we get into mechanisms, but the methyl shift. So all you do is you draw one of the methyls, it doesn't matter, starting at the methyl, and then go to there like that. Start on the bond and draw to that carbon that has the plus charge. Does that make sense?
Yeah.
Okay, so now what's happening between this one and this one?
There's a pi bond.
We are forming a pi bond, right? And so how do we form bonds? What do we need? We need an electron source, right? So where's our electron source in that?
The oxygen.
Oxygen.
Yep, it not just the oxygen, Joe. What specifically? Think back to the first step we did.
The lone pairs.
There's a lone pair there, right? There are two lone pairs, right? So remember, you always need to have something that you're coming from. So just draw a lone pair and then just come down like that.
But is there another step in that one? Because now the O and the H are bonded to each other.
The H and O were already bonded to each other.
Oh, yeah. Never mind. That makes sense. Yeah.
Does that make sense? Right. So they're still bonded. It's just in the next one we have to draw it because. So what's going to happen in between my last step? What's different?
You're gonna
Lose your hydrogen.
Mm-hmm. So basically, yeah, you're just going to lose that. So that's the big issue. So this is just going to pop off like that. Right. In reality, the water molecule we popped off earlier is going to remove it, but we can just do that because she hasn't told you how to do that yet. I don't know, but this is a simple way of doing that. Actually, hold on. Nope. That's bad mechanism pushing. So this water right here, when this right here that popped off, you formed a water molecule like this. And this is one of the most important things. So I have my many mechanism rules. Do you guys need a day of just mechanism teaching of how to do mechanisms? Do you need a video of that? Okay, there are some fundamental rules that you can always do that make your life a little bit easier in terms of if you follow them, essentially you minimize how big of a mistake you're going to make, right? So I have some fundamental rules that I learned from mechanism pushing. And if you do them, it's like, if you follow these basic rules, 95% of the time you'll be correct. So one of the first rules that we do is that what is true about the charge throughout the entire molecule?
Stays consistent.
Your charge, first thing, charge is always constant. If you change the overall charge of your molecule in some way without adding something, you have done something wrong, right? So plus, right? So now you're probably saying, but wait, what happened in that last step? So you made a water molecule here like this, right? So what's going to happen is that water molecule is going to come in like this and take that hydrogen and then kick that onto there. So then you get this product, but now you're going to have H3O. And what's the charge on this oxygen? Plus. So your charges always have to be conserved.
I just checked the answer key and she just put like the water and like the air in the last arrow.
Mm-hmm.
But I can't really tell like where, like how she removed the hydrogen. Because like she just kind of pushed a lone pair from the H2O to the H. But then like the charge never really got addressed. So no. I mean, I see how to do it, like how to get rid of the charge, but I'm just confused because like she didn't do it here.
Well, that's just because she may be teaching you a simple way right now. Like she might get more complicated a little bit later on. But I think if you learn this way now, you'll never be wrong. Mags, are you okay with this?
Yeah.
Okay, I see a question, probably from Matthew. Which part is the loss of a leaving group? So when did I lose something? When did I lose a functional group?
The second part, right?
Yep, because I lost the water. That's the leaving group. So anytime you form a positive charge like that, that's usually an indication of a leaving group leaving.
Okay.
Also, that H plus that is over the arrow in the first step, what type of reagent is that? It's an acid, right?
Yeah.
And most acids are what in organic reactions? I don't know if you've covered this yet or not. It's a C word.
Catalyst.
They act as catalysts. And so what is the one thing you guys, I know you know about catalysts?
They speed up
They
reaction.
speed up
They s-
reactions.
They speed up reactions, yes, but there's also something else about the catalyst itself.
Lowers the activation energy.
That's the same thing as speeding it up. But that's your same idea though. They always regenerate themselves. So I start with an H plus, I end with an H plus. That H plus is still there at the end. So if you ever have any type of catalyst, you need to make it, you can use it through reaction, but it has to be regenerated. Does that make sense? So the fundamental rules that I've taught you, your arrows always need to start at electron sources. Your second one is charges always must be conserved. And a sub one is that if you use an acid catalyst, it has to be regenerated throughout the course of the reaction. And this is true for any catalyst, right? They're not used up by the reaction. Melissa looks a little unsure.
Oh, I'm okay. I'm okay.
We can just punch her, say be done with it. No, I won't punch you. She's too nice. Even though I am afraid of about like 85% of Latinas, that number might be criminally low, might be above 90.
Why? I didn't do anything.
Because I went to school with plenty of Latinas, and I like to think of it as a healthy fear. Next thing you know, I got a chancla being thrown at my head.
That's my mom every time I do something.
Yeah, so at some point you guys are gonna slowly you might have that skill now and you've just never had to use it, and I don't want to find out. All right, so are you all good? Can I clear this, or are you guys still writing down?
Okay.
I'm good.
Okay. So another thing you could do is just, if you wanted to do this here, is that I guess you could just draw this bond going onto the oxygen like that, right? Like the bond is breaking if you didn't want to do that. But this is so you could have like the H plus here at the end. But the idea is that something has to remove that hydrogen, and it's going to be the water. And that was just me showing you that. All right, so let's go ahead and go down. Use curved arrows to show atom movement and draw the most likely structure after each of the following carbocation rearrangements. If it will not rearrange, state no rearrangement. So in order to have a rearrangement, what do you need to have adjacent to it? There's 3 situations where you're going to have a rearrangement. Well, technically 4, but I'm not going to bring the other one in.
1 degree, 2nd degree, and 3rd degree.
Kind of. You need to have something like either like a tertiary carbon or quaternary carbon adjacent to it, or you need to have a double bond adjacent to it. So is there any one of these that does not have a double bond, a tertiary or quaternary carbon adjacent to it?
No.
Adjacent to the plus charge. There is. One of them is.
Isn't it the last one?
Nope.
The first one.
It's the second one.
Oh, yeah.
Because you have this here, right? The double bond would have to be here. It has to be adjacent. It can't be 2 carbons away like it is here. You have to only be 1 carbon away from the end of a double bond. Does that make sense?
Mm-hmm.
So in this one, there will be no rearrangement because you don't have anything close enough to do it. Quick question. Have you guys talked about ring rearrangements? Ring expansions?
I think so.
You think so? Yay or nay? Okay, so I'll ask you this, and we've got about 5 minutes left. I know you're gonna bounce soon, Max, because of your birthday stuff. Yay! By the way, Matthew, it's Max's birthday, so make sure to wish her a happy birthday. As he's muted. But
Happy birthday.
Thank you.
Why? First off, are carbocations stable or unstable?
Stable?
They are very unstable. So carbocations are not stable. So remember, as we said before, chemistry, molecules and things like that are always trying to get to the lowest energy conformation. Stability is what they're driving to, right? So if you have an unstable molecule, it is going to do something to fix that. And this is why carbocation rearrangements occur. So if I have to have a carbocation, it's not ideal, but what type of carbocation is the best? Tertiary, secondary, or primary?
Tertiary.
Tertiary is my
Tertiary.
best one, right? Tertiary is going to be my best one. If it has resonance, it's even better, but tertiary. So what type of carbon is that carbocation? Primary, secondary, tertiary?
Secondary.
It is secondary. All right. So this carbon here is also secondary, but what is this carbon right here? Primary, secondary, tertiary, quaternary?
Quaternary.
It is quaternary. So here is a rule for carbocation rearrangements. If you ever have a secondary adjacent to a quaternary, you will have a methyl shift.
Oh,
So if you have a secondary carbocation next to a quaternary carbon, you are going to have a methyl shift. What that looks like is that this methyl group is going to move to there like that. And so now your new structure, right? This is where the methyl group moved, but now the group that lost the methyl, that is my new carbocation, like this. So what type of carbocation do we have now? Primary, secondary, tertiary?
tertiary.
It's tertiary. That's what we want to have, right? A tertiary carbocation is the most stable one. So does that make sense why this happens?
Yeah.
Okay. Melissa, how are you doing on that one?
Honestly, a little bit lost.
Okay. So just real quick, are carbocations stable or unstable?
Unstable.
Right. So they want to do something. So the most stable carbocation is going to be a tertiary carbocation.
Mhm.
So if I can do something to make a tertiary carbocation, I will do it. So if I go here to the whiteboard so that we have more room, when I think about this, right here, I have this. So as we said, I have a secondary carbocation adjacent to a quaternary. So whenever I have this, a methyl group is going to shift over like that. That entire methyl group is just going to go to that other carbon, right? And so now that methyl shift has occurred, this was the methyl. This carbon here is this carbon here, but now it has a methyl. I added something to it so it no longer has the carbocation. It's the charge is gone. This one here, this carbon is this carbon here. It lost the methyl group, so now it's the carbocation. But where here it was a secondary, here it's a tertiary. And so since I did this methyl shift, I went from a very unstable secondary carbocation to a relatively stable tertiary carbocation. Does that make a little more sense?
Yeah.
Okay. My thing's about to end. I need to change my laundry, so I'll be back in like 3 minutes, and then we will continue on. Mags, happy birthday. I will see you at some point next week, but we will come back and finish this dealy. So see you soon.
Thank you.
Happy birthday.
Thank you.